Yeah, I think the problem's gonna be pretty easy. It's gonna be based on.
Someone asked us because some outrageous something, and I'm sure somebody else has done it.
Yeah. I think we did it though. Remember when the shit was created or whatever? The one with that you couldn't get on I haven't read it.
He also posted a tutorial. Yeah, he posted a BBA tutorial.
Huh?
Is Tyler going to be?
No, he's out of town.
It is. Although he asked, it is the exact same problem. Yeah, it's the exact same problem. Yeah, this doesn't look too bad. I think this is.
Right, this one chicken.
No, he's in a coffee?
No, this is mine. You can have the coffee. Yeah, you can have the coffee. Yeah.
I think it's like
Grab this from you.
Yeah, no, this is yours. Because the sandwich line is too long. Robert, after class? Robert, after class? Sure. Alright. Oh, yeah.
I couldn't even sign up for it.
They'll make some response.
I'll be in.
Oh, right.
They'll make some response.
Yeah, no, you talk to Cynthia.
I just sent her an email.
I told you! I'm like, no.
I sent her an email because I need to register for summer classes, but I will be here to get advice in spring to be registered for summer classes. She's just permanently removed all the advice.
So wait, what are we taking? Wait, doesn't lab teach safety? Who teaches that? Did you teach it last year? Is it in a different semester?
Right now, the only class
Alright, let's start. Main subject today is actually moving of particles and drops of fluid to the terminal velocity. But before we get into it, let me briefly make a comment on the drainage flow in association with a few other problems that we have already worked on. And then I think you're very familiar with this problem. Initially, we do have a tank raised to a certain level, and then we go have an extended tube at the bottom of it. And then you're interested in calculating the flow rate, and at the same time, you're interested in how long it takes for the liquid level to drop. And then this one, I think before many years ago, I think we had a little gadget so that you can actually measure the time and do an experiment with benign water, and then it can confirm your calculation. That somehow that disappeared, and I don't know what that is. But anyway, homework number 5 has been posted, and so you do have some work to do during this holiday on Wednesday again, and that one is to calculate how the water level changes as a function of time. It's a transient case. Okay? And then if you take a look at the material that I posted, it does have a step-by-step instruction or guideline. So it's very, very specific. And you can just follow that instruction and have fun with it. Now, what I want to make a comment about is, some time ago we worked on a dimensional analysis of this capillary distributor. Here that we do fill the liquid with this bulb with a liquid. And then there are two markings at the top and bottom, and then you simply let the fluid drain, and then you measure the time it takes for the liquid level drop from this level to that level, and then liquid will flow through this capillary tube. And I adopted this one as a dimensional analysis problem where we do have these variables, and then you carry out dimensional analysis. And then later, there was an instruction saying that the experiment has shown that the time it takes for the liquid level change from here to here is proportional to the volume V. That makes sense. And then inversely proportional to the acceleration of gravity. If there's no gravity, then it's not going to come down, right? So if gravity is bigger, then it will actually move faster. But all those make sense. But and then it says, independent of the tube length L, H. In this case, H is the tube length over here. And then somehow, that one, I hope that some of you felt that it's strange that the time it takes is independent of actually the capillary length. Okay? So that was, so maybe at the time when this one was given as an exercise problem, nobody knew about it. But anyway, we derived an expression using that fact that viscosity being related with this. And I said that dependence on that R is very, very strong because it is to the fourth power. But anyway, the issue in this problem that I am raising is the fact that the time is independent of the length L, the capillary length. And then you may recall that we worked on a laminar flow through this pipe in a vertical one. And then at that time that we introduced the pressure drop, the pressure-driven flow, so we had a pressure difference from top and bottom, but at the same time, the gravity is also aiding to get that flow, so there is also gravity-driven flow. And then the solution is something that you are very, very familiar with. And then the whole thing in front of this square bracket is nothing but the maximum velocity, u maximum, that occurs at r equals 0 at the center. And then for this problem, for this particular problem, if you let the dynamic pressure being 0, in other words, if you simply let the fluid flow purely by gravity, then you will see that the dependence on L actually will disappear. For example, for this case, see the flow rate is a function of all these variables, yet there is no L appearing in here. The reason why L doesn't appear here is because for the purely gravity-driven flow, the pressure difference is proportional to the L because the static pressure increases with this liquid depth. Yet pressure drop actually decreases by L. Okay, so that L actually cancels out. In other words, the driving force as well as that dissipation actually cancels out. So as a result of it, then flow rate actually does not depend on the length L. So this one is a laminar flow case. And then of course over here that we utilize the fact that nobody raised a question about that, whether that is true or not, but I am pointing out that that is actually true. And then for this flow, that we did a calculation for various lengths of L. In other words, for the same flow situation, you change the length of the pipe, diameter being same, you simply change the length of it. Okay, so that one was homework number 4, I believe. Okay, and then when the length was 20 centimeters and 10 centimeters and then 5 centimeters, and then you do the calculation. And then you intend to see that velocity at the exit as a function of tube length L. It does change a bit. The reason is because there's a contraction and everything. Yet you will see that the dependence is very, very weak, whether it is 5 centimeter, 20 centimeters, or 30 centimeters, meaning that the average velocity is about 1.68. It changes to about 1.7. So 1.68 to 1.7 is a very, very small change, meaning the velocity V is nearly independent of the tube length L, which is seemingly very strange because there will be a frictional loss due to that. So if you have a long tube, then there will be a lot of energy loss as a result of it, and flow velocity may be lower. Okay? But that is not really, the dependence is not really that strong. Okay, and then in fact, now that you know the Bernoulli's equation, you can plot how the pressure changes as a function of position, vertical position. Right? Right at point A, it's an atmospheric pressure. Right at point B, it is atmospheric pressure. And in between, how does the pressure change? From A through this entrance, that you know that pressure would increase linearly because it gets deeper and deeper and deeper. Right? And then what happens is actually pressure from A to B, and then there's an atmospheric pressure. As you go down, this is a G direction, pressure actually increases linearly. But at the exit, it has to be over here. So what happens in between? In fact, if you calculate those pressure at this point, it actually drops right at the exit, and then it becomes like that. And many of you may find it difficult to understand at this moment about this, but that's the way it is. And then you may think about it, especially Joshua, you may think about that. But you always think, otherwise you don't really make big progress. I think it is the right attitude to think about it, raise a question about those. And then another thing that I want to point out is, instead of fluid, if it happens to be a bunch of solid particles, and then there is a very, very striking phenomenon occurring, and I was really stunned when I saw it for the first time long, long ago when I was a graduate student, as a matter of fact. And then when I went to a seminar, and then there is a well-known person who probably passed away, which is a couple of generations ahead of me. And then he just had a large the container, a beaker. I think it was a plastic beaker, so a big size, and it had a sand in it. And then he brought in a funnel, and then he had a long pipe. So in the beginning, he had a funnel, and then with no kind of extended pipe, and then he just would pour the sand, and then ask audience to measure the time that it takes so that the whole thing will be drained. So you measure the time. And then he actually put the extended pipe just underneath the funnel, so made the pipe long. And then he did the same experiment, and then asked people to measure the time, and what will be the difference between them. Normally, normal people like me at that time expected that it will take longer time if you have a extended pipe, longer pipe, compared to no pipe at all. Yet, strikingly, when you had an extended pipe, efflux time became a lot shorter. It actually drains faster. It's strange, isn't it? Yeah, but that's the way it is. Part of the reason is because of that motion of the solid, right at the neck region, air will be also sort of drained because of particle motion, and then suction is actually imposed on it. And so the pressure at that point becomes lower, and it sucks in, and then the particle motion becomes very, very fast. Yet, it's kind of challenging problem if you really can have to explain it, maybe theoretically, and then prove it, then it may be a rigorous work to do. Yet, there are many things like that in engineering, and then there are many things, sometimes you can improve processes in here and there. Although a lot of things has been there for a long, long period of time, does that mean that there isn't any room for you to make an improvement? That is not the case. There are still lots of things that you can work on and make the world better. And then I am asking you to, on Wednesday is a holiday, so instead of just whooping off, you spend a little bit of time and working on home number 5, and then just calculate how the height changes as a function of time. And then I've done my homework already, so I've actually solved the problem. So numerical integration of the drainage one. And I use the Visual Basic as a matter of fact. equation, which looks like this, is familiar to you. This H is associated with the liquid level height, and then fanning friction factor, and then these numbers. In other words, velocity expressed in terms of liquid height divided by some term associated with fanning friction factor, and then square root of it. You're already familiar with it, and then you work on it as a exam problem too, and then Reynolds number, and then fanning friction factor. This is the Brazos equation, the simplest form. By combining those, you can actually solve the problem. And then this one is nothing but the height change as a function of time is nothing but area times the volume. Okay, the volumetric flow rate. Okay. So using that one, then you can just write a group program. In other words, at each time, you can calculate what the velocity is. Using that velocity, you can calculate what the rate of change of the liquid height is. And then so for maybe a fraction of a second later, then the height has decreased. And then using that new height, you can calculate what the velocity is. Velocity will decrease gradually, or be very, very small. By repeating that calculation, you can plot the height as a function of time. So in Visual Basic, then you can have buttons or communication box or whatever. So I just wrote a program in macro, and then I click on a start button, and it will calculate up to 10 seconds. It doesn't show right in here. And I just created this communication box because these machines are so fast. Unless I stop somewhere, then it is going to calculate right away in a fraction of a second. And so just for the purpose of demonstration, it's asking me to continue, yes, no, and I say yes. And then again, all those can be embedded into the program. And then if you learn little things like that, then it can be very, very useful in your life as you work on simple numerical calculations.
Isn't it this viscosity of water is 1 sensor poise, right? Viscosity of water is 1 sensor poise, right?
Yeah.
Viscosity of water is 1 sensor poise.
1 centipoise, yeah.
There's-
That's 1 centipoise.
Yes.
10 to the minus 3 Pascal second is 1 centipoise. And then the density is 1 grams per cubic centimeters. That is 1 metric tons per cubic meter. Okay, so if I say calculate the whole thing, then it actually does plot and everything. So this is the velocity change, and the liquid height changes from 20 centimeters to nothing. It takes about 210, 220 seconds, about 3 minutes. Is it 3 minutes? 2 minutes. So literally 3 minutes and some seconds. So you put a little tank and then have a small pipe, and then doing experiment will be quite easy. And then you'll be amazed that such a simple calculation will actually match with the experiment. Okay? So the calculation that you have done, the stuff that you have learned is in fact is quite practical. You can use it at many, many different places. And in between, another thing that I want to point out is in calculating here that I have to confirm the Reynolds number over time. Because when Reynolds number is smaller than 2100, something changes in Bernoulli's equation. What is it that changes?
F.
Kinetic energy correction factor. Okay? To tell you the truth, there are few of you who didn't write anything on problem 3 of the exam. Although I told you many, many times the exact problem. Okay, it's a double whammy. That means that you didn't, not only you lost the point, but that indicates that you never came to class.
I thought you said there was going to be extra credit on the test.
Say it again?
I thought there was going to be extra credit on the test.
But anyway, now if you take a look at the Reynolds number gradually decreases. You see that it doesn't change much. So even all the way to the end, when the liquid level drops, Reynolds number is still very large. What does that mean? Transition from turbulent flow to laminar flow doesn't happen. Okay, but why is that? The reason is, although the tube diameter, I think for this case is only about 5 millimeters, still the gravity-driven flow, turbulent flow. Okay, I think there was also